The generator I built uses a polyphase stepper motor as a generator. The mechanical energy necessary for rotation is given manually by means of a crank coupled with two cogwheels. The generated current is then rectified and stored in a supercapacitor. Stepper motors are now widespread, and can also be recovered from old disused equipment. Various stepper motors are visible on the screen. Extracted from Scientific Instruments. Photocopiers, computers, printers and paper recorders of old type. R2, 3, 4, and 5-phase motors. All these motors can be used as generators, but the most suitable to use for this are those polyphase, 4 or more phases, better those with low operating voltages, around 5 volts and low resistance internal. From experimental tests, the current that these motors are able to provide is more important than their voltage. In a motor, whose characteristics are not well known, the phases must first be identified, and this can be easily done with a tester, identifying the two terminals of each winding. With the same tester you can also evaluate the order of magnitude of the alternating voltage output from the phases. Just rotate the motor shaft by hand. The tester will always indicate an alternating voltage. The voltage generated by each phase is individually rectified by a rectifier bridge, and we then proceed to the subsequent series parallel connections of the rectifier bridges, according to our needs. On screen a series of some series parallel connections, that can be used on 2-phase and 3-phase motors. In my generator I used a 5-phase motor, with 10 output wires. The diagram can be seen on the screen. The 5 rectifier bridges are connected in a connection mixed series parallel, which is what guaranteed me the best performance. To collect the electrical energy output from the generator I would have to use supercapacitors that are indispensable in this type of generator. Not having them available at the moment, I used the one that is a bit close to their capacity. 2 large electrolytic capacitors from 160,000 microfarads. In all I reach a capacity of 0.32 farad, and this allowed me to do the subsequent tests on the generator. The various parts that make up the generator are visible here. 1. Wooden supports. 2. Stepper motor. 3. Crank system mounted on an aluminum support with 2 bearings, and 2 gear wheels of 128 and 16 teeth, that allow a transmission ratio 1:8. Every turn of the crank made, the generator shaft makes 8 laps. 4. Printed circuit board with the rectifier bridges. Now the assembly of the system. Wooden supports are first fixed with screws. Then the stepper motor is fixed. Then the crank system is fixed with screws. At the end, the circuit with rectifiers is fixed. It remains only to solder the phase wires with rectifier bridges. The 10-stepper motor wires, welded at the entrance of the 5 rectifier bridges. Control of the waveform and frequency of the voltage generated by the stepper motor. The waveform is a perfect sinusoid. The frequency of the sinusoidal voltage, depending on the speed of rotation, varies from a few hundred Hz to a maximum of 1200 Hz. Control and measurement of the alternating voltage, at the ends of the motor windings. The voltage generated by the phase windings reaches a maximum of 7.8 volt effective. Control and measurement of the direct voltage at the output of the rectifier bridges, without capacitors. The voltage reaches a maximum of 18 volts. Evaluation of capacitor charging times. I proceed with the charging of the capacitors, up to the maximum allowed. 10 volts. After 22 seconds, I reached 10 volts. Now we turn on 3 SMD 5050 LEDs placed in series, with the charge accumulated in the 0.32 farad capacitors and observe how long they will remain on. After 1 minute and 18 seconds, the voltage dropped to 7.84 volts, and stepped from 3 diodes powered in series, to 2 diodes. After 2 minutes and 30 seconds, the voltage dropped to 520 volts, and this is the minimum voltage, below which the LEDs generate very little light. Practically, the 3 LEDs illuminated for 2 minutes and 30 seconds. With a supercapacitor of only 3.2 farads, I would have illuminated for a good 25 minutes. Conclusion. A charge of 3.2 coulombs is stored in a 0.32 farad capacitor subjected to a voltage of 10 volts. And to do this, I had to turn the crank for 22 seconds. It follows that if I replace it with a small 3.2 farad supercapacitor, this of 10 volts, it will accumulate a charge of 32 coulombs, and will be able to keep the 3 diodes on for 25 minutes. In this case, to charge the capacitor, I will have to turn the crank for 3 minutes and 40 seconds. Thank you for your attention. To the next.